All right. Good afternoon, everyone. We are going to be talking about electric fields today and also talking about a new concept of capacitors. So let's go ahead and jump into it. Let me see if I can pull up the homework problems today. How's everybody doing? I see Hannah has been playing chess today. I know that. She's been getting online, several moves. And my iPad is almost dead. Oops. I think our chess bracket's almost done. Although this last game's taken a while. We'll see how it goes. Hannah, did you win your other two games? Or how many games did you play? Yeah, Did you win your other games? No, it's all good. This game is just taking a little bit longer. We're like 30 moves or so, 30 some moves. So did you win your other games? So if Hannah won her other games, then it's just up to this game. So we'll see. All right. Noah just didn't play. Yeah, that'll do it. All right. So today, what am I doing? We are looking at field strength. All right. So we're going to check this out. Sample problem D. And electric field's not a super important topic for us, but I just thought I'd include it. We probably could have skipped it. But anyway, so we're going to be looking at electric fields and just doing a couple ones. The first one's pretty cool with proton and electron, right? So at that distance, you can imagine that the attraction between a proton and electron is going to be pretty strong. And you can do the calculation for the electric force, the force of attraction between them, or you can look at the electric field. So either way, it's just one more useful thing. So we talk about gravity is a force, is a field force, and electrical force is a field force. These are forces that are not contact forces, so you don't need to be touching. So your fundamental forces in general are field forces. All right, now let's go ahead and just jump right into number 2, because I think we skipped number 1. We didn't need to do number 1 for this one. So we're on number 2 in the homework. You got a proton and electron, and both of them have the same charge, and that the charge is going to be, so we can go ahead and write down our Q, because it's a proton electron, is going to be 1.602 times 10 to the negative 19th coulombs. So negative if it's an electron, positive is if it's a proton, whichever one you're talking about there. And then we have so they're separated by an average distance of 5.3. So we have an R value, so R, or distance, of 5.3 times 10 11th meters. Now, what is the magnitude and direction of the field, the electric field set by the proton at the position of the electron? Now, it could be a much more difficult question to talk about the total electric field at some other point. But now we're just going to talk about the one particular field at that position. So all we're really concerned about is the charge of the proton. And that's it. We don't need to worry about how the electron's charge is affecting it. All we're talking about is the electric field set up by the proton. So that's going to get us just a one-step problem here with the electric field, which is given by your Coulomb's constant times the charge divided by the distance between them squared, right? We're not going to worry about positives or negatives, but just worry about whether they attract or not. Let me see if I can get my light here better. All right, just worry about whether they attract or not, all right? And so this is going to give us, plugging in here, that's going to give us on what's Kc is 8.99 times 10 to the 9th newtons per newtons meters squared per coulomb squared. And then this is going to be times a Q value of 1.6 from 10 to the minus 19 coulombs all over this 5.3 times 10 to the minus 11 meters squared. And it's important that you work with the order of operations, get your parentheses in here correctly when you actually solve this. And so let's do that here. All right, we have 8.99 E9 times 1.602 E negative 19, all divided by, and we're going to go ahead and put this in parentheses, 5.3 E negative 11, and that's going to be squared. All right, that's going to get us a very large number. So 5.1, how many sig figs? Okay, so looks like we got disconnected there temporarily. Anyway, we're back. And so here we are. So we got 5.1 times 10 to the 11th. And now what are we talking about in terms of units? So we start off with newtons here, meters squared, and we got meters squared, so meters squared over meters squared canceled. And then we have coulombs over coulombs squared, so that's just going to be per coulombs. And so we're going to have newtons per coulomb as our units there. Okay, so notice how newtons don't cancel with anything. The meters cancel each other out. And you have coulombs on the top over coulombs squared, so it's just newtons per coulomb. So that's a pretty large number. All right. Oh, we got a lot of questions here. Yeah, to the international. Yeah. We got a lot of people timing out. Sorry, I just now saw that comment. I thought that was maybe about physics, but no, just about chess. Yeah. And I know a lot of the international students who traveled back to China or somewhere else, they were put in quarantine for some time. So they may not have been able to access the internet in order to play their chess game. Who knows? Anyway, so number 2, that's it. A very, very large electric field. And so putting any kind of charge in there, you're going to have a fairly significant force there. And so we notice that at these distances, the electric force is very, very, very strong. All right. Even stronger than that are going to be the strong force when you're getting to be even closer distances. But these are the distances where your electric force is very, very strong. All right. Now we're number 3. Let's go ahead and jump down to number 3. All right. We have an electric field that's already set up. So our electric field, let's go ahead and write down. Electric field is equal to, you got something different. So what'd you get? Oh, sorry, the direction. The direction is, and I don't think they tell us the relative placement, but the direction is, what is the magnitude and direction of the electric field set up by the proton at the position of the electron? And so we're going to say the electric field is going to be to the proton, right? Because they're going to be attracting each other. All right, and so the electric field is going to be attractive toward the proton at that point. So you get 27. Oh man, I don't even know what to say. It's possible. You know what I think? Oh man. What if you forgot to square the denominator? Let me try that out. If you forgot to square the denominator, let's just delete the square and see what happens. If I can delete that. There we go. Aha! If you forget the square, you'll end up with this answer, 27.17 something, which sounds a lot like what you got. So if you forget about squaring your denominator, that's probably what happened there. Yeah, that's my guess. That's my best guess. And so it's so easy to forget about those little squares, even though you write them down sometimes. Sometimes you just forget to put them in your calculator or something. So that's probably what happened. Anything else? All right, so let's go on. So the field at that point is going to be to the proton, so it's an attractive force. All right, we have, or I mean, we're talking about field, so it's an attractive field. Now, number 3, so we have an electric field of 2.0 times 10 to the 4th newtons per coulomb. It's directed along the positive x-axis. So basically, it's just going to be, positive along the positive x-axis. All right, and what's the electric force on an electron in this field, and what's the electric force on a proton in this field? So we have, in this case, and the number is going to be the same because they have the same exact charges, right? And so in order to calculate the force, so we remember essentially the electric field and the electric force are very, very similar. The electric field is just the electric force divided by the charge. And so if you want to calculate the force within a field, it's simply going to be the electric field times the charge. And that's it, okay? It's going to be the electric field, the strength of the electric field times the charge. And so we can go ahead and do A and B. They're going to be the same numbers, and they're just going to go in different directions. And the directions are not going to be too terribly important to us, but let's go ahead and work on this. So A is going to be 2.0 times 10 to the 4th newtons per coulomb. And we have 1.6 times 10 to the minus 19 coulombs. And this is going to be equal to our force. So the electric field strength times the charge. Let's see what that is. Okay, 4 times 1.602 times 10 to the minus 19th coulombs. And that's going to get us 3.2 and we'll just leave it at 2 sig figs times 10 to the minus 15. And our units, of course, are going to be what? So we have newtons per coulomb times coulombs. That's going to get us just newtons. And that makes sense because we're talking about force here. And if we're talking about force, it makes a lot of sense that the units are going to be in newtons. So you think that's a really, really, really small force, but we're talking about really, really small things. So if you're talking about electron or a proton, that force is going to be able to cause a very, very large amount of acceleration because the mass of both the proton and electron are very, very small. And the electron's mass is going to be even less. So the force on the electron and the proton is the same in magnitude. So A and B are really the same. And if we think about this as, so this is going to be positive along the x-axis, so along the positive direction of the x-axis. For A, that is going to be, what is A? A is electron, so this is going to be to the left. And then for B, so it's going to be directed back towards back towards 0, back towards the left of the x-axis because it's going positive to the right. Okay, and if it's going positive to the right, then a proton in this field is going to be repelled, and so it's going to be the same number, 3.2 times 10 to the minus 15 newtons to the right. Okay, and that's it. That's it for these problems. Shouldn't the electron charge be negative? Yeah, it doesn't matter. So they're going to be the same numbers anyway. All we need to worry about is it going left or right and that kind of thing. And so because the field strength or the field is moving to the right, and we talk about it in terms of a positive field, and so it's going to be an attractive field for the electron to go to the left, and it's going to be repulsive for the proton to go to the right. And they both have the same number. So we're not going to worry about positives or negatives in that one. Okay? So that's it. I want to take some extra time today to talk about capacitors and to talk about a little bit about electric circuits. So we're going to be talking about electric circuits today. The electric field, honestly, we could have skipped, but anyway, we didn't. And so we've talked about the electric force, which is super, super important. Negative left. Yeah. Right. Right. So we're talking about just electrical components for an electrical circuit and something like that. So we're going to be talking about that one particular component of an electrical circuit today, and that is a capacitor. Let me go ahead and just turn this over, and we'll talk about a capacitor. All right, when we're talking about electrical circuits, we're going to be thinking about things like batteries, and we've already, you guys should be familiar with batteries, and then we're also going to later be talking about resistors, and we're going to be talking about other kinds of things that can use electricity and all that kind of stuff. All right, and so the battery is going to be something that's going to be supplying some sort of relatively constant voltage. Okay, and so you might have like a 1.5 volt battery, a 9 volt battery, or something like that. Now, obviously the voltage of a battery is going to decrease over time, but they give a fairly constant voltage. No, you might be wondering, well, what in the world is a voltage? Okay, so voltage is, you can think of a voltage in a number of different ways, but a voltage is simply some kind of electric force, or more typically is called the electric potential. All right, sort of like similar to potential energy, but is not. It's not a potential energy. It's an electric potential, right? And so it's not necessarily actively doing anything. So a battery has a particular voltage, whether it's being used or not. All right, so an electric potential is more or less kind of like what we'd think of in terms of a physical realm as a cliff. Okay, so a cliff has some sort of gravitational potential there going on, right? So it's a gravitational potential energy, and you can think of the cliff itself as some sort of gravitational potential. All right, and so the gravitational energy wants to pull things down the cliff. And we oftentimes think of electricity in terms of water. And so if you're thinking of, let's say, a waterfall, the electric potential, that voltage, is basically an understanding of how high that cliff is, or how high that waterfall is, right? So the higher it is, the greater potential you have to cause that thing to come down, to cause that water to come down. Okay, a small cliff is going to be a small potential. A high cliff is going to be a high potential. And the same thing with voltage. Okay, the higher the voltage, the greater the potential. All right, and so later on we're going to talk about something a little bit more in detail, and that is electric current. So, electric potential. So your electric current is more like measured in amount of flow. Right? And so if we're talking about a waterfall again, so if you keep up the waterfall analogy, we're going to be thinking about, okay, how much water is going over? How much, let's say, volume or mass is actually going over the waterfall. All right, and so current is always going to be a measure of the flow of electricity, how much electricity is going over. And if you think of it in terms of a real system, right, this is going to be related to the number of electrons. All right, we're going to talk more about current later, and I'll talk about whatever units that we're going to be using for current and all that kind of stuff. Okay, so batteries set up, they have a certain electrical potential or electric potential, and that is going to be a constant voltage, right? And that's going to be kind of like this force or electrical force, but it's not really a force. It's electrical desire, or sometimes thought of as electrical pressure, but really is the electrical potential of that system, okay? And it's related to a cliff or a waterfall, all right? So what we're going to do is, let's say we take a battery, and I'll just go ahead and write this down in a very, very simple way, okay? And a battery, the symbol for a battery is going to be like this, okay? that itself is the symbol for a battery. And these two things are going to be wires coming off of it. All right, so this is a battery. That thing right there. All right, the small end right here is going to be the negative end, and the big end is going to be the positive end. All right, and so we don't need to worry about that too much right now, but what I want to focus on is, what if we connect this battery to something known as a capacitor? Well, what is a capacitor? So a capacitor is essentially two plates of metal. So connect this to two plates of metal, and it doesn't really matter what they are, and they don't necessarily have to be metal, but they just have to be conductors. All right? Well, what happens when you connect that to two plates of metal? Well, what's going to happen is you're going to get some flow of electricity. Now, it's going to be limited because this is not a complete circuit. We're not completing a circuit here, so you can have a constant flow, but you're going to have a little bit of a flow of electricity from that battery. And what's going to happen is the battery is going to cause, on the negative end, it's going to cause some electrons to come down this way, and you'll have some electrons piling up on one plate, right? So you have a negative charge on one plate, and on the positive end, it's going to suck some electrons out of that metal plate, and you're going to end up with some positive charge building up on this metal plate, right? And so anytime you have these two plates that are separated by a particular distance, or whatever that distance is, okay, so we have some sort of distance that's separating them, there's going to be an electric field that's set up by that capacitor, right? And that electric field, we could go ahead and calculate it, but we're not going to bother doing that. Instead, we want to focus on the capacitor. The capacitors, as we've drawn it here, have essentially a vacuum in between them, nothing in between them. But modern day capacitors are an important piece of, or important electrical piece of equipment, or have electrical function that are used in various different circuits, and they come in various different shapes and sizes, but typically they're not going to be just like this. What you can do is you can take those plates, so let's imagine this piece of paper is one of those plates, right? So a piece of paper is kind of the shape of a plate, and what you can do is you can just roll it up, right? And when you roll it up, all of a sudden you make that thing be able to fit into different things, shapes and sizes and all that kind of stuff. So you can take these plates and you can roll them up. But if you're going to roll them up, then you're going to say, okay, well, those two plates are going to touch and you're going to have a short circuit, right? You're going to connect the circuit, and that's not what you want. So what you need to do, instead of having them separated by nothing, you're going to put something in between, right? And you're going to shove, let me see, some kind of material in here. And that material is known as a oh man, I don't know how to spell this. I think is dielectric material, right? So you're going to put a dielectric material, and you go put that in between the two plates. Well, what is that dielectric material? All right, the dielectric material essentially is just an insulator. So it's not going to conduct any kind of electricity, but it's not just an insulator. What happens in the dielectric material is that you're going to get some rearranging. So let's go ahead and write it this way. Okay, so if we have a plate here, let's do this. So we're going to look at it, we're going to turn the plate so you're going to look at them straight on. So plate. This is going to be our positive plate. This is going to be our negative plate. And in the middle, we're going to put our dielectric material. So the first purpose of the dielectric material is to make sure the two plates don't touch, right? But next, what the dielectric material is going to do is it has electrons in it too. And those electrons, although they're not free to move, they can move a little bit. They're not going to be able to flow. So the material itself is not going to allow free flow of electrons from one end to another, but it can, let's say, maybe orient the molecules a little bit, or it can have a little bit of change in how it's oriented like, let's say, water molecule, okay? Now, a water molecule is a polar molecule, right? And so if you orient the water molecule a certain way, so let's suppose it was made out of water. No, water is not good to use here because it's a liquid, right? But let's suppose we were to use water. And in that case, you would have the water that would be oriented like this. And you would have the partial positive hydrogens on the right and the partial negative oxygen on the left. And it'd be oriented all the way down the middle through that. And so without having any kind of flow of electrons, you have an orientation change of the dielectric material, which causes you to have a temporary buildup or a dipole of the charge in the material. And so what you have is you have a set up a little tiny bit of negative charges in the dielectric material and a little bit of positive charges on this side. Again, you can't have any flow, but you have this set up. And so when that dielectric material has a change in the orientation of its molecules, you now have this set up, and what happens is that actually does two things. It increases, well, it firstly insulates the material, and secondly, it increases the capacitance. And why does it do that? It enables you to pile on more charge and have the things closer together in order to have this buildup of charge, and it decreases the electric field between them because of this dielectric effect. Okay? So that's your capacitor. And essentially, typically what your capacitor is essentially you've got two plates with dielectric material, and you take those and you roll them up and you shove them into something, and that's your capacitor. All right? It's used, and you can read through your book, it's used for a number of different things in electrical circuits. Very, very important. So now let's get to the actual equations. The equations are not hard. They're fairly straightforward. So you have C, your capacitance is equal to Q over V. Now I do need to mention what in the world these things are. So Q is the charge of both plates. All right, and so we're going to just take the absolute value of the charge. We're not going to worry about positive or negative, okay? So it's the absolute charge of both plates. Now we're assuming both plates have the same charge, okay? Now it's going to be a little bit more of a complex situation if they don't have the same charge, but in any kind of system that we have imagined so far, if you hook it up to a battery or something like that, they're going to build up the same charge. Okay, so you're not going to you're not going to add them together. It's just simply going to be the charge of either one of those plates. All right, so we're not adding, right? It's the charge of just one plate, which is the charge of the other plate. Okay, that's what Q is. V, this is going to be the voltage. Okay, why is it delta V? Because it's emphasizing that this is a potential difference. Remember, this is a cliff. This is that difference in potential of your two different things, right? It's how much difference there is between this positive end and that negative end. It's got to do with the chemical reaction that is potentially going on inside the battery, right? That's your voltage, it's your potential difference, right? And so you can calculate that. One more equation that I do need to give you is the potential energy. Because capacitors themselves, when they're charged, when they're in use, they have a certain amount of electrical potential energy. And the electrical potential energy of a capacitor is equal to 1/2 Q delta V. And you can go ahead and maybe you don't have, let's say, Q. And if you don't have Q, then you can go ahead and solve for Q using this equation and say, okay, well, Q is C times delta V, and then just plug it in there and you can get a new equation for that. Or let's say you don't have delta V, and so you can say, okay, well, delta V is going to be equal to Q over C, and you can plug it in for that. All right, and so you can use this equation and substitute in for different things and rearrange it as you like, but simply put, the potential energy is 1/2 Q times delta V. All right. So let's go ahead and do our sample problem. Your sample problem is on page, what is it? 964. 964. And I want you guys doing some reading. The reading covers voltage and talks more in detail about what voltage is really all about. And you guys can do that reading on your own. But page 964, so that's like a lot further down. So let me get to that real quick. All right. And we're almost done. We're going to probably have, I think we're going to plan for, let's say, a test maybe next Wednesday, and then be all done and not have any class on Friday or anything like that. If that's not going to work for you guys, we can just make the test on Friday and do nothing on Wednesday. All right, so plan on tentatively having our test, our final test. It's not a final, but our last test next Wednesday. Okay? All right, where is it? 964. Okay, so here we go, 964. And yeah, white balance gets all messed up when I show this. But anyway, so you have a capacitor that's connected to a 12-volt battery. All right, so as we're going through the sample problem, sample B, right? 12 volts, well, what's that? That's the voltage. And so we're going to say our delta V is 12 volts. And it holds 36 microcoulombs of charge. Now, don't forget this, okay? So don't forget what these different prefixes mean. And that's going to be our Q is 36 microcoulombs. All right. And it's asking us how much, what's the capacitance and how much electrical potential energy is stored in the capacitor. And we have this information. All right. So let's go ahead and do it. Now we can go ahead and just leave this as 10 as a microcoulombs, but you need to really, really remember what that means. So this means 36 times 10 to the minus 6 coulombs. You're going to find your book is going to mention maybe some other prefixes too. And let me go ahead and remind you, okay? So micro is 10 to the minus 6, nano is 10 to the minus 9, and pico is 10 to the minus 12. All right? So those are some prefixes, micro, nano, and pico, that you might find. And the reason for that is when we're talking about capacitance, we often have fairly small numbers. All right, so let's do it. The capacitance in this case is going to be Q over delta V, and that's going to be Q is 36 microcoulombs over 12 volts. Fairly easy math. Don't even need a calculator for that. Now you could, if you wanted, put that in your calculator as 10 to the minus 6, or you could simply say, okay, well that's going to be 36 divided by 12. That's going to be 3, right? And that's going to be microcoulombs per volts. Now we do have a new units for capacitance, and that is Faradays, right? So not Faradays, farads. 1 farad is 1 F. 1 F is 1 coulomb per volt. Okay? And so we could say, in this case, this is 3 coulombs per 3 microcoulombs per volt, which is 3 microfarads. And that's the units. Right? Or you could say this is going to be 3 times 10 to the minus 6 farads. All right? Last part of this, what's the potential energy? Potential energy of this capacitor once it's charged up is going to be equal to 1/2 Q delta V. And Q, we said, is 30. So it's 1/2 times 36 microcoulombs times your 12 volts. All right? And let's go ahead and calculate that. So it's essentially going to be 36 times 6, or you have 1/2 times 36 times 12, and that's going to get us what? It's going to get us 216. Now, keep in mind, that's what? That's 216. But is 216 times 10 to the minus 6. And we're going to want to head 216 times 10 to the minus 6. And what are our units going to be? Well, we have microcoulombs, and we have, so coulombs times volts. Our units here are going to be the same units as any other kind of energy units, and that's joules, right? So we shouldn't technically leave it as 10 to the minus 6. We should take that and move it over. Sorry, running out of space here. That's going to be 2.16 times 10 to the minus 4 joules, all right? And that's going to be our potential energy of this particular capacitor. All right, so we're all done. So today we've done capacitance, and then tomorrow, I think tomorrow we'll talk about resistors. All right, see you guys. Any questions before we sign out here? I'm not sure I put the homework up yet, but just in case you want to know what the homework is, let me see. It's going to be so 17B and number 1 to 3. Okay, so I think there's 4 problems. Just do the first 3. So problems 1 to 3, 1, 2, and 3. And I'll go ahead and put that up on Google Classroom right now. All right, anything else? Does the exponent matter with joules? No, you could technically write 216 microjoules. That'd be fine here, or just 2.16 times 10 to the minus 4 joules. You could write 216 times 10 to the minus 6 joules. That's fine, as long as you don't forget this micro here. And if you just erase that and you said 216 joules, that'd be way off. When's the next chess tournament? I don't know. Do you guys want to do another slow tournament? Because our slow tournament, the second round is going to get started probably pretty soon, but not right away. Do you want to do another slow tournament, or would you guys like to do like a fast tournament, like a live tournament? And we can do the fast tournaments different ways. We can make them 10-minute games. You can make them 15-minute games. You just can't make them too long, because then everybody's sticking around for hours waiting for other people to finish. So that's the main reason why when you do the live tournaments, why we try to keep the time down. Yeah. So I would be up for another fast tournament, just like a live tournament where we show up. But last time we did that, not too many people showed up. If people are interested, so Adam, if people are interested, we could do that. Just play like 10-minute games, 15-minute games, whatever people want to do. Cool? All right, I'm going to go ahead and sign out. And if you guys have any questions, just email me. I'll see you guys back tomorrow. Have a great rest of your day. See ya.